I'll leave you with one. This is shown to be optimal from a theoretical context. It's a principle that underlies the Monte Carlo tree search. It's the principle of optimism under uncertainty. So I hope you and your listeners will take that with them. I think sometimes I feel a little bit of a lack of optimism when reading the news and so forth. But even if it's a delusion, I believe that going about your life with optimism is if all of your variables are, let's just say, binary, they're just true or false, yes or no, you have lung cancer. If you have 100 of those variables, then you're going to have 2 to the 100 different assignments. And there's just no way you can try to estimate all of those, the probability distribution over all of those combinations from any kind of data set. 2 to the 100 is ridiculously large.
It's larger than the number of atoms in the universe, right?
Yeah, it's just not feasible. You could do it with maybe 5 variables, the Bellman equation, which is, in my opinion, the most beautiful equation of all time. I don't know what your favorite equation is, but when I ask people in the class, some say, oh, like Euler's equation, e to the pi I plus 1 equals z. That is a pretty nice one. There's
pretty
E equals
cool,
m,
yeah.
F equals ma. There are Maxwell's equations. Those are all very cool, but I'm quite partial to the Bellman equation because it defines what it means to make an optimal decision under uncertainty.
All right, Mykel, thank you so much for being here. This is amazing.
Yeah, sure thing. Thanks for the invitation.
Of course. As I mentioned privately, I mean, I'm unapologetic about CS238 being my favorite AI class. And just in terms of the applicability of the concepts into day-to-day issues, and it really transformed my way of thinking. And I think really made probability more accessible to me. I didn't have a very strong math background going into the class, and this really gave me a practical appreciation for the concept. So first of all, thank you for that. and secondly, I think you have the incredible experience of having developed incredibly high stakes software with tons of different stakeholders. And I think the story of your contributions to air traffic control systems and traffic collision avoidance systems maps the story of AI quite well, going from something like TCAS to something like ACAS-X. I think really translates the narrative from like what people thought AI was in the 50s to what people think AI is today. But I want to put us in a dramatic entrance to the highest stakes dogfooding your own software situation ever, which is when you're testing to see if collision avoidance systems works on a plane. So why don't we start there? What was that moment like, and sort of put us in the context of what's going on?
Yeah, so the concept of ACAS-X kind of just evolved from initially equations on a whiteboard, and then it turned into a much larger program with the support of the FAA and many other organizations and so forth. But in 2013, the FAA and Johns Hopkins Applied Physics Laboratory and Lincoln Laboratory supported the first flight test of the ACAS-X software. And I was on the original flight, and that's when it started feeling real. There was a lot of modeling and simulation for years leading up to that moment. A lot of simulations of what would happen in different scenarios, probing all the different kinds of edge cases, but it suddenly became real when I was sitting on board that aircraft.
And just so people have an idea of what we're talking about, so this is software that runs on a system in airplanes that alerts pilots to what to do in case there's a likelihood of a collision. Is that right?
Yeah. Yep. Yeah, and it'll instruct the pilots to climb or descend at a particular rate. So that's the version that has been developed for manned aircraft. There have also been other versions developed for larger unmanned aircraft and small unmanned aircraft.
And well, first of all, I mean, just the stakes of this is incredibly high, right? So this is the I'm thinking of like analogy to something like a day to day parking radar. You know, it's the parking
Yeah,
radar for cars, but in a situation where the speed at which things develop is much more critical, and there's the human panic component that we have to account for too, where pilots may react in a weird way, and sort of the system accounts for that so that it only warns you at the right only when it needs to. um, so that's incredible. And why don't we talk about some of the differences between TCAS and ACAS-X? So ACAS-X is your contribution that, I want to get into decision making under uncertainty and computational decision making. But TCAS, the preceding system, had a different flavor of it, right?
yeah, it's a very different kind of approach. And one thing that I should emphasize with ACAS-X is that even though I led the original research effort, many people were involved
Mm.
in making that reality. But they represent fundamentally different kinds of approaches. So with TCAS, it's very much rule based, and that
Hmm.
placed a lot of burden on the human designers to anticipate like what you should do in every possible situation. But the problem with that is that the space of possible scenarios is just so vast. You have to reason about, the different kinds of approach angles. Um, uh, you need to be robust to the other pilots turning suddenly. You have to accommodate sensor error and so forth. And so it placed a lot of burden on the really smart people who worked on TCAS back in the 1970s and 80s and so forth. But I should also emphasize that TCAS has been a major success story. There, uh, since the introduction of TCAS, there have not been any mid-air collisions in the United States involving a TCAS equipped aircraft, and that's just spectacular. And today, one of the safest places you can be is at 30,000 feet in an aircraft.
Which is just an incredible accomplishment of human engineering. Um, and not only in that it's just a remarkable implementation of a safety protocol, but then that we
Mhm.
keep striving forward and we keep trying to push forward and try to get, more sigmas of performance out of a system in which we're already, as you said, this is already one of the safest places on earth. And so I think it's fascinating that the FAA and in general technology companies are starting to become more aware of the benefit that AI can bring in terms of safety when humans are placed in positions that they're naturally very bad at reasoning at. So these very low probability events of everything going wrong, you hitting all the wrong things in the span of 30 seconds, the human brain completely freezes and paralyzes in fear, whereas a mechanized system has a better probability of figuring these things out. So this is a good segue to talk about what ACAS-X does and what the bigger framework that it sits under, which is decision making under uncertainty and computational decision making. Which I, having reflected on it a bit more, like I think that's, it really cuts close to what intelligence is, like just the abstract concept. So I wanted to ask you, decision making, take it away. What is it, and how do you think
Yeah.
about it in the abstract?
So if you want to make good decisions, whether it's about medical decision making or aircraft collision avoidance or automated driving or whatever, you're making decisions in a sequential manner. And the decisions that you make now will affect the state of the world in the future and what actions would be available to you in the future. And you have to take into account a few different things. You need to be able to take into account the stochasticity or inherent uncertainty about the outcomes of your actions. Right. So if you start climbing in your aircraft, then it may or may not have some kind of impact on what the other aircraft is doing. Or in the medical context, if you administer a drug to a patient, you're going to be uncertain about the outcome of that drug. So there's outcome uncertainty, there's uncertainty in the state. So you often don't have perfect state information.
Mm-hmm.
So what a state is just a snapshot of the true state of the world, right?
Mm-hmm.
So in automated driving, that would be like the positions and velocities of the other vehicles and pedestrians and so forth. But you don't always get to observe that perfectly, right? There might be a big truck in front of you that's occluding your ability to see a pedestrian, or your LiDAR system might have some noise, or it might fail, or whatever. In medicine, you don't get to directly observe the true state of the disease. Rather, you make these diagnostic tests and you can try to help reduce your uncertainty in the state of the disease, but it's not going to be perfect, even with the best imaging and DNA sequencing or whatever. And then the other challenge in these decision-making problems is you often have to balance between multiple competing objectives.
Mm-hmm.
So, for an example, in aircraft collision avoidance, you want to balance between the alert rate and safety, right? You want it to be extremely safe, right? But if your system alerts as soon as you encounter another aircraft, then no one's going to use it, and you won't get the benefit of having that system.
Mm-hmm.
And it turns out that humans are not always very good at reasoning over long time horizons, especially when there are low probability events. This has been well studied for decades.
And so you mentioned the uncertainty part to a good degree, right? Like we really are working with imperfect information. We're trusting our sensors, even just human beings. Like we're trusting
Yeah,
our sensory input, knowing that we can fall prey to optical illusions or all these kind of audio
right,
illusions. And we start building this model of the world, right? Like we think the world works a certain way, that if we behave with certain types of conventions and customs, the outcomes are going to be what we expect, and we navigate this world, and we have this mental representation of the dynamics of the system and how we are agents in the system. And you mentioned something else, which was we do have competing objectives too. I want to stand out, and I want to blend in, and like all these very real personal drives. So I think like a good place to funnel the conversation towards is maybe this idea of utility. That in the space of decision making, maybe like the coarse way to talk about it is that we want to find the decision that maximizes the value for us, right?
right,
Um,
right.
so, is there more to it? I mean, like we could get to the philosophy of utilitarianism and utility theory and all that stuff, but I think like maybe like a cursory overview of your thoughts on utility and how you think about that.
Yeah. So when I present the basics of utility theory in our decision making class, I start off by outlining some of the original axioms on rational preferences. And
Mhm.
these were introduced by Oscar Morgenstern and John von Neumann back in the uh, mid 1900s in their very famous book, Theory of Games and Economic Behavior. And
Mhm.
so, what they posit are just a handful of axioms, such as if you prefer A to B and B to C, then you have to prefer A to C. So there are
Mhm.
axioms like this, right, that
Mhm.
sound pretty sensible, I think, to most of the students
Mhm.
who I teach. And then what they were able to show is if you accept these sets of axioms, then there has to exist a real valued function called
Mm-hmm.
a utility function that allows you to compare different outcomes, your
Mm-hmm.
preferences for different outcomes. And that if you're uncertain about an outcome, you can actually assign the uh, utility to that uncertainty, and it turns out to be just the expected utility over those resulting outcomes. So you
Mm-hmm.
weight the utilities of the different outcomes by their likelihood. And then from that, uh, I introduce the principle of maximum expected utility, which
Mm-hmm.
is the maximum expected utility principle underlies much of economics. It's fundamental to artificial intelligence and so forth. So in our course and in my textbook, Algorithms for Decision Making, this is the key, that's the key principle.
Mm-hmm.
And what we present in the class and in the book are computational methods that allow you to try to maximize that expected utility. Turns out that this can be very challenging to do for many different kinds of problems, and you have to rely upon different kinds of approximations in some
Mm-hmm.
cases.
Yeah, and I want to get into all the stuff that sort of builds up on that, because I think the foundations by themselves are just so interesting in terms of, like, if you think about them a bit more, you start toying with ideas like morality, which I was surprised to find in this very simple framework of you imagine a set of possible next states given my actions.
Yeah.
You extract the utility functions, like, so then you can rank order them in terms of preference, and then basically the maxim is always pick the one that gives you the highest utility. Um, and that basis of rationality, and also maybe in terms of basis of morality too, because it's what you should be doing, right? At least in this theoretical framework, right?
Yeah.
And so now we're in a very interesting space to talk about decision making and agency, not just as people, but also as in the systems that we design, right? And I want to echo your textbook, which is one of my favorite textbooks that I've ever bought, in terms of how it makes the material really accessible, and it always blends theory with application. And so you're
Mhm.
always sort of like held into, coupled to reality, and not running away with like abstract thoughts. So I really appreciated that. And I think it does a remarkable survey of the space. Okay, so now we have this idea that we want to select the action that will maximize our return, let's call it. And we start the class to CS238 by parameter learning, right? So the way I read it is, we see these distributions of events happening in life. Like we flip a coin and we try and estimate, whether the coin is fair based on the outcome of those coins, right? Um, so how would you describe parameter learning as the perceptual space of something that we're gonna evolve into a decision making framework?
Great. So we originally introduced the concept of parameter learning in the context of learning the parameters of a probability distribution.
Hmm.
So how do you assign numerical values to the different outcomes? And so for an example, if you're wanting to estimate the probability that a coin will come up heads, you can flip it a bunch of times. You can collect that data, maybe um, 54 times out of 100 it comes up heads.
Hmm.
Then what we've been doing ever since kindergarten is our estimate would be 54 divided by 100, or 0.54, right?
Hmm.
Now what we did in the class is we tried to uh, arrive at a quantification of our uncertainty in that estimate, right? It's not going to be exactly 0.54, right?
Hmm.
In
Right.
fact, the true probability is it's going to be some real number, right?
Hmm.
And so what we tried to do was apply Bayes' rule, uh, uh, a very famous, very simple rule that underlies much of science, to the problem of estimating parameters. And a nice byproduct of the mathematics is that we can get an analytic distribution, an analytic function that describes that distribution. So it'll assign more probability mass to values near 0.54, but it'll also assign, smaller amounts for other probability values. And it allows you to really quantify your uncertainty. If you want to, you can convert that probability distribution over parameter values into like a confidence interval. Like maybe you'd be able to say that with 90% confidence, the the probability is between point, I don't know, 0.45 and 0.72 or something like that.
Mm-hmm. Yeah, I think of it as, and it's just so interesting to me, this idea that you can have probabilities on probabilities. So
Yeah.
you don't know what the probability is, but you're trying to find what is the probability that this is the probability that manifests the reality that I'm seeing, right?
Yeah, exactly. So probability distributions over probability distributions, that's a conceptual leap that we tried to make in that class. But I think one way to think of it is you're trying to estimate your uncertainty, and you need
Mhm.
a way to quantify your confidence in that estimate.
It makes total
It's
sense. I
still a
mean, like,
lot.
no, but once you see it, I mean, it just makes so much sense, especially when you think about like expected value and things like that. So it just becomes something, another number that you need to multiply your expected utility by to know how confident you are on your predictions on the
Yeah.
space, right?
Yep.
Um, and okay, so now we're sort of dealing with this very, I think of it as the perceptual level where it's just we're looking at the numbers and we're trying to we're looking at raw numbers and we're trying to see like what is the probability distribution of those numbers. And then the next layer of the class was structure learning, and I think that gets into, so like Bayes' rule deals with dependence of probability of random variables, right? So in the case of now we want to see how these numbers are related if we're looking at many of them, right? And then it starts to get interesting because we start building these graphs and like these models. Okay, so we're parameters. What's the next leap in terms of structure?
Yeah, in terms of structure learning, what you want to be able to do is capture the relationships between different variables. So a lot of the pioneering work on this actually originated in the 1980s in the context of medical decision making. So in medicine, you have a whole bunch of different variables. Some of these variables you can observe more easily than others. So for an example, one variable would be like, is the patient a smoker? Another variable is, have they developed lung cancer? Another would be, uh, do they get more than 6 hours of sleep? Another one would be, I don't know, blood oxygen levels or something like that.
Mhm.
And then from uh, a database of data, you can try to infer the relationships between those variables. And as part of the class, we learned a technique for figuring out uh, what those relationships are.
Mhm.
And so you can go from a large database where you don't know what the relationships are with some kind of maybe human interpretable kind of explanation for the relationships between those variables. Maybe there's a connection between smoking and lung cancer or something like that. And what that allows you to do, okay, it allows for some amount of interpretability, but it also allows you to reduce the number of parameters that you have to learn from your data set. So there's a
Mhm.
fundamental trade-off between um, having very flexible probability models that allow you to capture, all the different kinds of relationships between variables with the ability to learn them from a finite amount of data.
Um, and there's a hidden component there which I think is really interesting that you run into very very quickly. That is the asymptotic complexity of these problems, right? So when we're dealing with 5 variables, we can easily imagine like the space where we're comparing any of those 5 to any other of those 5. But as you
Yep.
get to anything bigger than that, like 5,000, then it starts to become it's quadratic at least, and
So
so
if you
then.
try to, if all of your variables are, let's just say binary, they're just true or
Mhm,
false, like yes or no, you have lung cancer.
mhm,
If you have 100 of those variables, then you're going to have 2 to the 100 different assignments.
mhm.
And there's just no way, there's no way you can try to estimate all of those, the probability distribution over all of those combinations directly from any kind of data set. 2 to the 100 is ridiculously large.
Yeah,
But if you,
like for context, it's larger than the number of atoms in the universe, right?
yeah,
Um,
yeah, it's just not feasible. You could do it with maybe like 5 variables.
right.
And so when you get to larger numbers of variables, you're going to have to make what are called conditional independence assumptions.
Hmm.
Um, and in order to do that, we explored different ways of identifying conditional independencies directly
And
from the data.
I see. So so the way I think about it is like you're building out a space of possible configurations, and you're
Mhm.
narrowing down which parts of the space are more likely, right? Based on probability on the data that you're seeing, these configurations are more likely. But there's another term in terms of structure that is the graph that is built. So the abstract notion that one variable is connected to another variable, and there is a quantity, there is a modifier, a numerical modifier to that relationship. So now not only do we see the relationship, but we also see how they're related. And I
Exactly.
think like we were all doing this during the pandemic when computing in our brains, like, oh, I saw this person 2 days ago and they coughed 3 days ago. So what is the likelihood that I should test? And then if I test, what is the likelihood that the result is going to be right in the context of changing information? Um, and so that gets us from raw observation, a bit of structure, there's a bit of a dependence relationship, to Markov decision processes, where now we take this graph and we sort of try and apply our reasoning around actions to it, and state transitions. So what is the likelihood? I think of it as a factoring in the time dimension, right? What is the
Yeah,
relationship
exactly.
between, right? Like,
Exactly.
um, and okay, so Markov decision processes, one of the all-time most epic things ever. What are your thoughts?
Right. So the idea of Markov decision processes, they date back to the work of Richard Bellman in the 1950s, at least back to the 1950s. So yeah, you're right. They're a way of capturing the time dimension. It's the standard mathematical model for sequential decision making under uncertainty. And so, in order to define a Markov decision process, you need to specify, what's the space of possible states. So maybe it's positions and velocities of other aircraft or pedestrians or cars or whatever. You need to specify your space of possible actions or decisions that you can make, like steer left or right, accelerate, decelerate. And you need to define 2 other things. One is your state transition model. So, what's the probability distribution over your next state, given your current state and the action that you take?
Mhm.
And the last thing that you need to define is your reward model. So, there needs to be some way to quantify how good or bad a different states and actions are. So, for ACAS-X, of course, you get a very large penalty for collision. You have smaller penalties for alerting. For medical decision making, maybe you have a huge penalty for a bad patient outcome. Maybe smaller penalties or costs associated with different diagnostic tests, which may or may not be directly connected to like the financial cost, but maybe that also factoring in the risk to the patient. Okay, so that defines the problem. The state transition model, the reward, that defines a Markov decision process. Once you have that model, you can employ a number of different kinds of techniques for solving it. The approach that was suggested by Richard Bellman in the 1950s was called dynamic programming. And there are different forms of dynamic programming. One that we focused on in the class is value iteration. So it's a really simple algorithm. It's iterative. You can write it down in maybe 6 lines of Julia code or Python code. It doesn't matter. But it's an iterative algorithm. And in the space of it of course depends on the size of the problem. You're able to solve like a problem with 40 million states in a few minutes. So the original ACAS-X problem had 40 million states. We could solve it in about 6 minutes. It's
Wow.
a very flexible kind of algorithm. I should not emphasize the importance of getting the transition model and the reward model right. Right? If you put in the wrong parameters to your reward model, like if you don't penalize collisions enough, then of course you are going to get undesirable behavior. But if you take the transition model and the reward model as truth, this will give you the optimal solution. So that iterative algorithm implements what's called the Bellman equation, which is, in my opinion, the most beautiful equation of all time. I don't know what your favorite equation is, but when I ask people in the class before I show them the Bellman equation, some say, "Oh, like Euler's equation, e to the pi I plus 1 equals 0." That is a pretty nice one. There's E
Pretty
equals
cool,
mc
yeah.
squared, F equals ma. They're Maxwell's equations. Those are all very cool, but I'm quite partial to the Bellman equation because it defines what it means to make an optimal decision under uncertainty.
Yeah, and I want to riff on Bellman's equation because I know every time I've seen you academically and online, you geek out about the Bellman equation. So I want to spend some time getting there because I do think it encodes something magical, right? Like when you get to the level where you have the representation of an MDP or Markov decision process, and you're trying to reason through it, Bellman's equation captures that.
Yes.
But you mentioned something about reward, which goes back to this original idea of utility.
Yes.
So I want to say there's like a layer of informed expertise that has to go into determining the utility of these certain things, even not just in subjectively assigning rewards to outcomes, but even the distribution of those rewards. So, for instance, is death minus infinity, or is death zero, or and then you're suddenly like playing with these ranges, the domain and range of this function, where you're really playing with concepts at the limit, especially in the high stakes situations that you're dealing with, either healthcare or air traffic, and so there's like an interesting blend there between the insights of experts and machine systems who, as of yet, do not have the evolutionary dopaminergic infrastructure built out to determine what they should prefer over what not to prefer. And okay, so we're dealing with this graph that represents the set of states the world can be in and the actions that we can take in each of these states. And we want to essentially climb to the state that maximizes our reward, right? So that is just a great abstraction over the decision making space. And one of the things that makes it, well, it's kind of fantastic that we can write it down as an optimization problem that has an exact solution. And this is like, we can mathematically, this is what Bellman's equation does. It just says this is how it works.
Yeah, it's actually quite remarkable because the space of possible decision-making policies it's exponential, right? It's exponential in the number of states, right? So if you have, um, let's say you have 10 different states, 10 different decisions, and you only have 100 different states,
Mhm.
right? And that's a relatively small problem if you only have
Tiny,
100 states.
tiny, tiny, tiny.
But the space of policies would be 10 times 10 times 10, 100 times. So it'll be 10 to the 100.
Mhm.
And you can't search that space of possible policies and just pick the best one. It's infeasible. I mean, you can write down the optimization problem, and yes, a solution does
Mhm.
exist. But what Bellman's equation does is actually it says that you can find the optimal policy in a polynomial amount of time, it turns out.
It's
And that,
incredible. I mean, it's so cool. And there's something that I also really love about the idea of dynamic programming, that it blends many different facets of computer science into alignment. So it brings the idea of recursion. It brings the idea of, I mean, like at the systems level, all these compiler optimizations to make recursion efficient and fast, um, and and even in, like, instruction set, branch prediction and all that stuff. So it's a really cool concept that has, driven a lot of beautiful smart ideas. But I wanted, so let's talk about the Bellman equation itself a bit more, because people can
yeah,
look it up and, like, and it's pretty simple, right? um,
yeah, it just like all those other equations, it's incredibly simple. Well, once you understand it, you won't ever forget it. It's an equation that you can't unsee.
yeah, you wanna give us a little taster?
Yeah, so basically what it does is it allows you to compute the value associated with being in a state, or the utility associated with being in a state. And in a sequential problem, the utility is just the expected accumulation of reward into the future. So
Mhm.
remember the reward function. In sequential problems, you care about the sums of the rewards over time.
Mhm.
And one thing that I should really emphasize here is that the rewards are subjective, right?
Mm.
That and we'll only get policies that optimize your own subjective reward, or the reward
Mhm.
of the designer of the system in an engineering context. Okay, so we're trying to figure out what that utility is. If we figure out the utility of the optimal solution, then we can actually pull out the optimal decision-making strategy. But what we have on the left-hand side of the equation is the utility associated with the state. And then on the right-hand side, what we do is we try to find the action that maximizes your immediate reward plus the expected reward into the future. To figure out the expected reward in the future, you have to reason about all of the possible next states. That's where the transition model comes in, right?
Mhm.
And so you weight all of the possible next states by their likelihood from the transition model. And you're computing an expectation over the utility of those next states. So you have the utility of states being on the left-hand side as well as on the right-hand side. And what the Bellman equation does is it says that you have an optimal value function when you have when it's an equality. So you can use that equation to you can apply that equation iteratively. And what you can do is show that you will converge to the optimal value function. Once you have the optimal value or utility function, it's used interchangeably in the literature, you can pull out the optimal decision-making strategy.
It's just so interesting. So the one way to think about it too is there's this graph of states that we're dealing with, and we're trying to paint the graph with
Yeah,
the color that is. So, given that I'm in this particular state, what is in the vicinity of states, like the what places that I can land based on where I can do now, which of those is preferable, even though there may not be a feedback, a reward function for any of those, right? So um, I don't get to win until the touchdown is scored, but what is the
that's right.
thing that, the thing that increases the probability to get a touchdown, right? And so that I'm sort of
Exactly.
financing my reward, by modeling it into the state that is right next to me, even though it's not, where the reward actually lives. Um, and so that
Right.
gives
So
you this.
in many engineering problems, as well as life and sports and so forth, there's sparse reward, right? You
Mhm,
can go a long time before you actually get a reward. Um, maybe you have seen that in your schooling. Maybe you have to study a lot until you feel the reward of understanding. And then what you have to do is figure out uh, what you have to assign some credit to the states that bring you to the later on states that do have a large reward. And the Bellman equation lets you do that.
mhm,
It's telling you what are the values of these incremental states that might bring you to where you want to go. And it does it in a way that takes into account all the different sources of uncertainty in
mhm.
your state transitions.
And there's another layer there, which is the discount from the future. We see this in economics too. The idea that, money in my pocket today is better than money in my pocket tomorrow, because of the returns that I could get on that money. And the same idea applies here, right? Utility today is better than utility tomorrow, not only because of the uncertainty that you may not get it tomorrow, but also, I guess that one's a bit more subjective. Why is it better today? Um, but there's another parameter there that is like how badly or
Yes.
intensely you discount the future. And you may be in certain, depending on the problem space that you're in, that parameter would look different. I don't remember getting into that too much in the class. Are there some rules of thumb there that are interesting?
Yeah. So in the Bellman equation, there is a discount factor.
Hmm.
Before you take the expectation of the next state, you actually discount that
Hmm.
that return. And yeah, you can think of it as an interest rate. Uh,
Hmm.
it you can incorporate that in order to account for uncertainty in the future. It also a nice byproduct is it keeps your solution bounded, right? So imagine a problem where you just get a reward of one at every step.
Hmm.
If you
I see.
don't discount it and it's an infinite horizon problem, what's your utility
What?
going to be? It's going to be
Infinite.
infinite, right? And then you wouldn't be able to compare a policy that gives you a reward of two at every step versus a reward of one at every step because the utilities would be exactly the same,
Hmm.
just positive infinity. And so discounting
Hmm.
is often used. So how do you choose that discount factor? If you're dealing with money, then maybe you can have it relate to an interest rate. But I think typically people try to set it, reasonably close to 1.
Mm-hmm.
There's a bit of a trade-off, though. The
Mm-hmm.
closer you have the discount factor to 1, to having it basically undiscounted,
Mm-hmm.
then you will need more iterations of the Bellman equation to arrive at an optimal
Mm.
solution, which kind of makes sense because when you aren't discounting as much, then you have to look further into the future.
Right.
If you're discounting heavily, then you don't have to look out as far.
Right. It makes total sense, right? In terms of if I value the future as much as I value the present, then in order to make the right decision, I have to look really far out into the future, which costs imagination,
Yeah,
power.
exactly.
Uh,
Yep,
but if I value the present more highly, then all I need to do is calculate my local network of possible next states.
yep.
That makes total sense. And this reminded me, I want to make a note of, there was a really cool example in the textbook about a mathematical way to simulate humans' irrationality. I forget exactly what it was, but there was like an exponential. I forget.
Yes. Yeah, logistic level K or logit
Yes, yeah.
level K. Yeah,
And so that, like, maybe this is a digression from the big line of questioning, but we operate under the assumption that humans are rational. That economics is based off the premise that humans make rational decisions, but we everybody knows that their life is probably way more irrational than they would care to admit. And
yep,
I think it comes to this idea of reasoning through low probability events, right? Where the brain just can't, it struggles at the limit of things that it's never seen before, incredibly unlikely coincidences. And so how does this model, the logic K model, help fudge rationality so that it closely matches humans way of reasoning?
right. So we introduced that model, and I should emphasize that model is just one of many different kinds of models
Hmm.
for modeling human behavior. But what it captures is the uh, finite capabilities of a human in a multi-agent context. So the level K part is when I'm making my decision, I'm thinking about what decision you're going to make, but in the process, I'm modeling you, modeling me. And so the
Hmm.
level K is like I think that
Hmm.
you think that I think, and so forth. Empirically, it has been found in some interactive games that humans are about 2.5.
Hmm.
They play at a level of 2.5 on average. But on top of the finite nested reasoning is the logit model, which says that you make errors in lower consequence kinds of situations, and it allows you to it incorporates into the model a probability distribution over possible actions. So you
Hmm.
don't model the other person as being completely rational, but
Hmm.
rather with some probability they'll take a suboptimal action, and that likelihood is related to uh, the the amount of consequence.
I see. So it's the modifier is the stakes or the utility of a given state,
Yeah, yeah.
which makes
It's
total sense.
it's, a,
Like,
it's
yeah.
an imperfect model, right? It's just a
Oh yeah,
mathematical
it's.
model that many people have found useful.
Mhm.
It's mathematically tractable. You can describe it in just a few equations, and that's it. Of course, you
Mhm.
can come up with much more sophisticated models with way more parameters, but then you'll need more data in order to justify that model.
Mhm.
So what you can do is build up these models of interactions with humans, with different degrees of rationality, and you can pull that into the Markov decision process when you go about optimizing your own system.
Mm-hmm.
So any of the systems that we design in the real world may have to interact with human decision makers, and it's
Mm-hmm.
important to properly model the humans in the system.
Mm-hmm.
You
Totally.
can't
This
just
goes back to the
necessarily-
ACAS-X example of
exactly
of pilots reacting, like if they're or being overly sensitized to an overly alerting system. Um,
exactly. So you have to capture the human behavior in the optimization of your engineered system.
mhm. And another note to what you just said in terms of it's a simple enough equation that models an aspect of human behavior that we want to capture, right? That we want to be
Yep.
able to reason around. And I think that brings up an interesting point about your branch of AI, very different from language models, where it's trying to capture the je ne sais quoi of human consciousness and Turing test passability. This is a different kind of approach where you're trying to distill away the core components of what makes a good decision in the utmost abstract. It's almost like this is how you should think about thinking, and
Hmm.
then the computational aspect of okay, what are the computational limitations of the space? Even if you can model it, even if you can imagine it, it doesn't mean that you can compute over it.
Yeah.
And so I
Yeah.
think it's cool to have the first of all the awareness of it, but also the flexibility of saying, "Hey, we want to try these different human simulating mathematical functions that have different constraints on them." And this was one of them that I remember was so simple that was I thought it was really cool. In terms of the meta reasoning, multi-agent system reasoning type of way, and it's almost like how does this reduce to that was my reaction when I first read it, and then I want to get into the second point, which is when faced with the gigantific, unbelievably infinite space of possible futures, the techniques that have been employed to reason or to prune that space, to chop down that space into manageable
Yeah.
complexity, a lot of them use randomness. Um, and sort of forfeit the thorough computation. You're not going to do the full agent reasoning of somebody else, but you're
Yeah.
just going to say, okay, imagine that person takes a random action. Or that not just that person, the system, the transition, the action uh, gives me a random result. And so it opens up this idea of our relationship with randomness in decision making that I wanted to explore with you. So before we get into something like Monte Carlo systems, which are
Yeah.
like more developed, let's talk about randomness in decision making.
Yeah, so randomness is a good way to arrive at approximations. So instead of trying to, exhaustively search an exponentially growing space, you can sample that space. And these so-called Monte Carlo methods have been explored for doing those kinds of inferences and optimization. So one area where this has shown tremendous value in decision making is in a method known as Monte Carlo tree search,
Mm-hmm.
where you run random simulations of different policies, and you those random simulations allow you to build up a search tree that allows you to go deeper in the areas that appear more promising. So this is the approach that was used by DeepMind, that was later
Mm-hmm.
acquired by Google, to solve um, Go. So Go, the game Go, the ancient
Mm-hmm.
game Go, was for a long time viewed as like impossible for AI to solve. Back when I was an undergraduate here, they were saying, yeah, sure, they may have been able to solve chess. So IBM's Deep Blue beat Gary Kasparov in 1997. But a lot of people said, oh, that's because the computers were able to exhaustively search, down to a reasonable depth, and that's why it won, not because of any special AI.
Hmm.
Uh, but Go is a different thing because the branching factor there is just so large,
Hmm.
um, and to handle that branching factor, uh, it turns out that this form of Monte Carlo tree search was the key insight, or a key insight. It also combined aspects of neural network function approximation and so forth, but this contributed to that success.
And
We found it useful not just for Go, but also wildfire fighting and many other applications that we've been exploring in the lab.
and it, to me, MCTS was one of those ideas that stuck with me
Mhm.
forever in terms of the and just this very, I don't know, it's very powerful to me, the idea that you can engage with randomness to derive the whatever, a very ordered solution, right? And then you dig deeper and you find that this is based on law of large numbers and things like that, where you're actually just discovering the true distribution of things by reasoning through this I guess random forest walk type of behavior, and you're finding out it's a faster way to crawl the space where you're sort of, I want to say, you're getting a sense of the energy of a given direction that you're going. So like if
Yeah.
there's three choices and those three choices could lead to very different places, I don't uh, I don't have to imagine making the perfect choice all the way. I just have to get an idea of, like this is the life that this could lead to if I choose to go into industry or go into academia or go into the arts, right? These are very different sort of vibes. And the reason I want to use this like imperfect language is because the method uses, I don't want to say imperfect, but like this thing that we can't understand, which is randomness.
Hmm.
Um,
So it's
and
not completely undirected randomness. Built
yeah.
into Monte Carlo tree search is the careful balancing of what appears to be promising and exploration of things that you haven't tried out so much. There's the exploration versus exploitation trade-off, and
Hmm.
that's core to that algorithm.
And to make that a bit, to bring that back to the example before, I could be deeper into imagining a life as an academic, but I spend
Hmm.
some of my cycles imagining a life as an artist or imagining a
Yeah.
life as a
Yep.
and sort of like what is the, before I'm in too deep in any of one of my choices, I still want to hold on to that model in case I want to change my decision or in case I want to like move closer in one direction or another.
Exactly.
And then there's all these other cool things about MCTS, that there's like these numbers that happen to work, like the square root of two. I remember is there in as one of
There is a square root in there. Yep. Um, inside of the square root are the counts of the number of times you've tried a particular action from a particular state, and
right,
that's part of
runs.
the exploration bonus. So you get
Mhm.
a little bit of a bonus to when you explore paths that are underexplored. But you still want to bias it towards paths that appear promising.
Mhm. Right. So it's an incentive to daydream, is how I think
Yes,
about it. Right.
exactly,
Um,
exactly.
and okay, so now we're almost at the final, at the crowning moment of the arc, which is um, we have parameters, we have the structure, we have the Markov layer on top,
Hmm.
where we have states and state transitions and actions, and then we get to the real state of affairs in the world, that is partially observable Markov decision processes, or how do POMDPs? Is that how you
Yeah,
call them?
POMDPs. Yeah, yep.
POMDPs, and that, if ever if I've ever heard a concise summary of how to go about thinking about life, it's life as a POMDP. And
Yeah, actually, it's the let's see here. It's our here's our lab T-shirt. Our lab is the Stanford Intelligent Systems Laboratory, and on the back it says "Life's a POMDP." And I think the reason why uh, this sticks in the mind of the students in the class is because yeah, the lives that is because yeah, that's rife with uncertainty by a regular Markov decision process, but also uncertainty in the state, right?
Mhm.
You, um, the key innovation in the POMDP over a regular MDP is the partial observability. They don't get to observe whether I don't know the person they have a crush on, what they think about them, or uh, that they're uncertain about whether they'll get a job offer.
Mhm.
And of course, all of these different sources of uncertainty create a lot of anxiety inside of them. And I think also the idea of exploration and like finding the appropriate level of exploration when trying to optimize their life's trajectories, that also resonates with them.
And when I also think it's like a very, I think it's a beautiful discovery in terms of like if you set out in the ambitious project of trying to distill what the right decision making is under the worst kind of constraints, and then you find that that is the problem that the human computer has been solving for billions of years. I think is just both an exciting, empowering, and aligning
Mhm.
thing where we are doing this. We have our sensor readings. There's the temperature in the air, humidity in the air. There's my metabolism. There's the photons that are hitting my retinas, and I'm trying to everything else on top of that is something that I've imagined,
Yeah.
or that
Yep.
we've sort of collectively imagined and helped each other imagine together, um, to build a model of the world that leads to where we're at today, where we can be having a conversation. Um, it happens that we're very, very closely by co-located, but we could be anywhere in the world at communicating at the speed of thought. Um, and and so it's incredibly cool, and also I think it proves um, it has this very humbling component too, which I think is that you're dealing with partial observations. You're never actually peeking at the true state, the true,
Yeah. Yeah.
but the illusion of believing that the state is true is an incredibly convenient one, because if you're not, if well,
But it can be quite brittle.
it can be so brittle, and I think there was a collective sense of, oh wow, this is really, really brittle, that I think um, was accentuated in the past few years, given all the stuff that's going on in the world. And there's some remnants of that today.
Yeah.
But this idea that, oh wow, the collective organization of society is this very subjective thing,
Mhm.
and that I think that there's a cool inspiration there about everybody still trying to guess, or derive the correct state and socialize that in the right way, so that we collectively find the state that we're in and the state that we want to get to together. um, and so it's just incredibly cool. I mean, I guess it was one of those proverbs that just stuck with me. And okay, so now we have a model for the entire problem of decision making, which is cool that it applies to computers. If you want to code this out in algorithm, and there's like an incredible literature there in terms of how to apply this in industry or for any research problem that you want. And then
Yeah.
there's like the personal lessons that I take out of it, which is like, how does this apply to my decision making? Um, so given that framework, you run the Intelligent Systems Lab at Stanford.
Mhm.
What are some of the problem spaces apart from air traffic collision that your lab is working on?
Yeah, so we work on a wide variety of kinds of problems. We sit in the aerospace department. I'm an aerospace professor, and naturally, many of our problems are aerospace. We've had a number of great collaborations with industry and government research labs. We have a couple projects going on with NASA. So one project is with NASA Ames, which is just down the street from Stanford. And that's in support of the Viper mission, which is being launched to the moon next year, 2024. And the idea is to find water ice on the moon using a rover. Our collaboration has focused on how do you do the reactive planning for that. So the rover is equipped with a radar sensor, a drill, mass spectrometer, and so forth. The rover needs to reach certain locations at certain times so it can um, unfurl its solar panels and recharge. But it also needs to be able to react to the scientific information that it gathers along the way. So there's an aspect of needing to plan for uncertain results that it will get in the future. So that's one collaboration with NASA Ames. Another one is with NASA JPL, the Jet Propulsion Laboratory down in Southern California. And that has involved underground exploration of caves and so forth. This originally started out as the DARPA Subterranean Challenge. We collaborated with NASA JPL on this. And we look at issues of how do you rapidly explore an underground environment when you have a suite of different robots? How do you maximize coverage? That requires reasoning about your global exploration of the environment as well as planning within your local environment and taking into account uncertainty and traversability of your region. But we've also done work on automated driving. We've had really wonderful collaborations with Toyota, Ford, Honda, Nissan, and so forth.
Um, I mean, also, as you were saying this, I mean, it just goes to show how broad the applicability of the. I mean, it's such a general framework that that it applies to so many different spaces. You also had mentioned privately healthcare decision making when routing ambulances. Um,
Yeah, but routing stroke patients to different locations. So the question arises: do you take them to the just the nearest hospital, or to maybe a further away hospital that can do a thrombectomy to remove the blood clot and so forth? Lots of very high stakes decision making. We've also been working towards different sustainability efforts related to hydrogen storage, geothermal, mineral exploration, and so forth. That's a massively growing area for us as well.
And in the case of the healthcare situation, my grandma just had a stroke. Since we
Oh,
chatted,
sorry.
and so we literally like that was part of the discussion. And but it's the type of decision that you don't want to make as a human. You want the
Yeah,
optimal
yeah,
solution, right? Like you just want to
yeah,
trust the process. And it goes to me asking like this next question that like, um, so you collaborate with these incredibly diverse and mighty stakeholders, whether it be JPL, which has layers on layers of constraints, NASA, the FAA. Anything related to healthcare has so much red tape around it.
yeah.
So, first of all, how did you manage to successfully navigate those partnerships over and over again? Let's start there.
So I think with all of these collaborations, it was real. the initial phases was to really understand their problem and respect their problem and really learn their language, right? We also have we have work in finance, and that's a whole other uh, that they have their own nomenclature for uncertainty and so
The
forth.
Greeks.
So part of it is learning their language, and then and figuring out what are the metrics that they care about. So for the FAA, they care about what's the risk per flight hour, um, and also understanding what are the baselines, what can we compare against. And for stroke patient transport, there are the different states have different guidelines on how to do these transports. For aircraft collision avoidance, we conveniently had TCAS as a very, very good baseline.
Mm-hmm.
And then what we do is we build up a simulation capability so that we can evaluate, thousands or millions, or in the case of aircraft collision avoidance, tens of billions of scenarios. And we look at the metrics. We evaluate the metrics that they care about. And we can say, this may, our research indicates that maybe doing things a little differently will result in this benefit. Um,
What, did you want
how
to
would
give it
you
a
like
go? Yeah.
how would you like to proceed? But I think another part of it is just the communication of the solution methodology. So the various stakeholders need to be able to trust that the approach you're taking is sensible and grounded in something that's real and
Mhm.
that can be interpretable, right?
Yeah.
So for these very high stakes systems, whether it be in finance, medicine, whether it's the control of planetary rovers, they don't want to trust in an AI black box.
Mm-hmm.
It's not enough to say, oh, we ran it with this deep neural network and TensorFlow output this result. That's not going to fly for these domains. For some domains, that might be just fine. If you're driving, if you're using it to produce, online
Marketing
ads,
copy.
then sure, fine. Or if you're using it to predict what, I don't know, what dress size to recommend to a customer,
Mm.
um, sure, fine. But when lives are at stake,
Mm-hmm.
um, when high stakes scientific missions are on the table, yeah, you need to be able to establish that level of trust.
There's a beautiful sense of truth in these ideas, just deep mathematical truths, and I think it's one of the it's certainly a lot more accessible to most people than having to not even getting into like deep learning models, but even just breaking through the initial phases of linear algebra, where you're now sort of like algebra was already a stretch for a lot of people, and so like then you add matrices and you add sort of calculus on top
Yeah,
of that, it
yeah,
becomes very abstract very quick. Whereas
yeah.
I feel like with these equations that we're talking about today, they become, they remain pretty concrete because you always have a sense of what the numbers map to. In a deep neural network, you have no idea what the numbers map to, as soon as you start training.
Yeah.
Um, and but I could also imagine there being some spaces where the blend of both could be incredibly exciting, where you're running
Exactly.
MCTS, and at each node you have some sort of deep learning agent reasoning around stuff stochastically, and you can explore the space there. I mean, I don't. None of them are coming to mind right now, but I bet that could
Oh,
be fun.
well, Go, in order to solve Go, they had to use a neural
Oh,
network. To
sure.
solve Atari, they use neural networks. Um, I have I have nothing fundamentally against deep neural
Yeah.
networks. In fact, it's a major ingredient in some of our applications. It's just that for some domains, if you can get away without using a neural network, then that's the way to go. In
Mm-hmm.
other domains, like if you have like computer vision, if computer vision is involved, like high dimensional perceptual systems, then the state of the art is to use a deep neural network of some
Mm-hmm.
form, or a transformer for natural
Mm-hmm.
language processing, or whatever. But it's important to really understand the pros and cons and limitations of different kinds of representations.
Mm-hmm. No, it's super cool, and I've also been excited about the blend of. I think just LLMs have captured the zeitgeist, and I think that there's a more exciting future where we blend LLMs with these
Exactly.
other frameworks that are already proven to be successful, and where we don't have to reinvent a computational graph of states over,
Yeah.
translating language into some other space where we can just use the weights that have already been discovered there.
So one aspect that I'm really excited about for these LLMs, I mean, it has really captured everyone's imagination. But what it does well is it encodes a tremendous amount of common sense knowledge.
Hmm.
And if you're a robot interacting with the real world, in order to do anything sensible, you need to have some level of common sense. Like
Hmm.
that milk is often found in a refrigerator, or
Hmm.
something like that. Trying to encode that all by hand, it's not going to work. And so these LLMs can encode that kind of common sense knowledge that would be useful for modeling the transitions in a Markov decision process. For an example, like if I do this, then these different things might happen. That could be derived from the output of an LLM.
Hmm.
That said, of course, right now especially, we have seen LLMs hallucinate and
Yeah.
provide, unreliable outputs. But I think that there still can be a tremendous amount of value that we'll see brought into the research
Hmm.
involving POMDPs and so forth.
Ah, it's so exciting. Okay, I want to end with a bit of trivia stuff. So we've talked
Yes,
about, the bulk of it, but there was a side component there in the class too that, and I've gathered since that you're pretty involved in and a big fan of the Julia programming language. Um,
yes, yes.
so let's talk Julia. I love non-mainstream programming languages, and I love talking to people who love them. So let's talk about Julia.
So I originally was introduced to the Julia programming language before it even went into beta. It was originally developed at MIT by a PhD student, Jeff Bezinson, and a few others. It I was very hesitant because as a computer scientist, I thought, the last thing the world needs is another programming language. And it was being suggested to me by a couple of people from the Johns Hopkins Applied Physics Laboratory. They were suggesting it to me as a language to represent the ACAS-X system. So we
Mm,
were working on building a prototype, a hardware prototype of the system. I had originally done an implementation in C++,
mhm,
uh, together with a few others at Lincoln Lab. And we were originally going to translate it into pseudocode
mm.
for Johns Hopkins to
Implement
implement
their own, yeah, yeah.
it into real-time C code. And from that experience, I tried my hardest to make unambiguous um, pseudocode. But
Hmm.
it turns out that, despite my efforts, that there were ambiguities, and you just can't have ambiguities when
Hmm.
you're designing an avionics system. And so I started thinking, oh, well, maybe instead of pseudocode, we just do it in Python. We provide a high-level description in Python,
Hmm.
and then instead of having um, this person at Johns Hopkins call me up and
Have to
disambiguate,
disambiguate. Yeah.
then I can say, just run this function.
Hmm. Hmm.
And also in parallel, Johns Hopkins Applied Physics Laboratory, they were working on the verification and validation aspect, in particular formal methods of analyzing the system. And they suggested using Julia for both the specification and for the verification. Julia because it can synthesize its own parse trees easily. And it also turns out that Julia is very, very fast.
Hmm.
Um, it sits on top of LLVM, which is the modern
The
compiler
C
framework.
compiler.
It's the framework for that underlies Clang. It's
Hmm.
maintained by uh, the open source community and heavily invested in by, I believe, Apple.
Hmm.
And so I implemented the key routines in Julia, MATLAB, Python, and compared it to my C++ implementation. And Julia was pretty close to the C++ implementation.
Wow.
Python was just not in the ballpark. So the Python has really taken off
Hmm.
in AI and machine learning. A lot of the standard machine learning toolkits are in Python, like PyTorch
Hmm.
and, and so forth. Um, there are also pretty good linear algebra and
Hmm.
scientific
NumPy. Yeah.
libraries, NumPy, SciPy, and all that. But for some applications, you really need to write for loops.
Right.
and and if you have programmed in Python, you know that things slow down really quickly. It's not built for that.
No,
It's like
no.
Python
Scripting
is
language. Yeah.
it's a scripting language, a glue language that glues together um, APIs that are typically written in C or
Hmm.
Fortran or whatever. And Julia can also serve as a glue language or a scripting language, but you can also just write fast code in Julia,
Hmm.
and you get the performance of another compiled language.
Hmm.
In Python and MATLAB, I did a lot with MATLAB back when I was at MIT Lincoln Laboratory. But what the process would be, you prototype something, it runs too slow, and then you would take the key computational part and then re-implement it in C++ and create
Hmm.
a MEX,
Wrapper
a
around it. Yeah.
library that you call from MATLAB. So you have the two language problem,
Right.
and
Yeah.
Julia helps us solve that two language problem. It's
Hmm.
also a very elegant language. It
Hmm.
handles multiple dispatch, which is very interesting from a computer
Hmm.
science perspective. It's very clean, very
Hmm.
flexible, um, and so I view it as a very nice first language, and it's the language
Hmm.
that we use in our textbooks. The one on the new one on decision making, as well as our 2017 book on optimization.
Hmm.
In pseudocode, you can look at the Julia code, and it's very close to what you would write down in pseudocode, or um, yeah, it's built to be human interpretable.
Super readable. I remember very accessible. We used it for the class,
Yeah,
and I remember
yeah,
there was virtually no learning curve. Sure enough, I was at the stage where I was already a polyglot, and so this was
Yeah,
this
yeah,
was familiar to me. But in a world where you're going to be learning this stuff, I think that and it was cool to me to see in terms of like the open source community how Julia navigated bigger projects like what used to be IPython notebooks that now are Jupyter notebooks because of
yeah,
Julia, right? Like the rebrand, the Jew is Julia, isn't it?
yeah, exactly. Yeah, JU, Julia, Pi for
Right.
Python, and R for R.
For R, yeah.
And one of the benefits of Julia is that they learn from the innovations as well as the mistakes of prior languages.
Right.
Uh, so, and you can actually trace many of the design decisions on GitHub tickets
Hmm.
issues. So you can
That's pretty
see
cool.
all of the discussion about like why are you using one-based indexing instead of zero-based indexing,
Hmm.
like with C. Um, but yeah, it's fascinating to track, and it has turned into a really wonderful community.
And one last bit to touch on there, that the libraries for Julia allow you to do this type of literate programming that I'm
Yep.
guessing is how you formatted the textbooks, probably even. Um, so it's able to um, really beautifully and elegantly present the code in a way that is almost like a manual, like an operator's manual for the code, as opposed to just some random slash comment uh, on the code.
Yeah, it supports that. For our textbook, we did it in LaTeX and embedded the Julia code. And when we go to do the compilation, it compiles that code to generate all of the figures. We actually don't have any external figures. Everything gets generated on the fly with that code.
Oh, that's so cool. Um, No, it's great. Michael, all right. I think we're
Yeah,
almost out of time. Should we close it with one last question?
sure.
What is some advice that you might give for anybody listening who is either beginning their journey in terms of AI or
Mhm.
computer science or better personal decisions? What are some of the takeaways from the past few years that you were willing to share?
Right. So maybe I'll leave you with one. And this is shown to be optimal from a theoretical context. It's a principle that underlies the Monte Carlo tree search with the exploration bonus and so forth. It's the principle of optimism under uncertainty. So I hope you'll you and your listeners will take that with them, and because I think sometimes I kind of feel a little bit of a lack of optimism when reading the news and so forth. But even if it's a delusion, I believe that going about your life with optimism is the way to go.
Amazing. Perfect. What a way to end it. Michael, thank you so
All
much
right.
for your
Thank you
time.
so much for the invitation and having me on.
Of course. See you soon. Bye.